Okay, welcome back, kiddos. This is part 2 of our installment in the video lesson for Guided Notes, Unit 3. We're learning basically about atomic bonds and how they form molecules and why they form molecules. So, a little review of what we just did. The concept of a mole and Avogadro's number, 6.02 times 10 to the 23rd. We talked about the difference between atomic mass and molar mass, or molecular mass. Atomic mass being measured in AMU, or atomic mass units, the weight of a proton or neutron, and molar mass being measured in grams per mole. Okay. And then why do bonds form? So we're learning about the concept of electronegativity, and what I have down here is a small version of an electronegativity table. So each, and I'll zoom in, but it's going to be hard to see, it'll be blurry. But each element, okay, so here's the periodic table as we're used to seeing it, yet listed up here are numbers that are not the atomic numbers, the number of protons, but a value giving the electronegativity, or the amount of pull on an electron. So noble gases in general don't want electrons. The halogens want electrons a lot because they have 7 valence electrons and really want an extra 8th. So you can basically write 1, 2, 3, 4, 5, 6, 7, and that will correspond to the number of valence electrons that each of these elements in each of these groups has. Okay, these ones in the center, the transition metals, they are sort of more complicated, and you can't just look at their place and know how many valence electrons they'll have, so you're basically not going to have to know that. We'll talk about metallic bonds in a moment. But given the number of valence electrons, and knowing that an atom basically wants 8 in order to be happy, except in the case of hydrogen and helium, because they have just one energy level, they want 2. But everything here, okay, these guys, they all want 8 valence electrons in order to be happy. So they want an electron more than anything, and these are sort of second in terms of how much they want electrons. These really want to give away this one electron, because if they give it away, then it's bumped back to the previous row and all, or the previous energy level, and all of a sudden they have a full shell. Okay, and then these want to give away 2 electrons, not nearly as badly as these, but they definitely want to give them away. So for electronegativity, again, that's a measure of the pull. It's a number, okay, and it's a measure of the pull of atom on electron. Okay, so pull, I'm going to say pull on electrons. So high values for electronegativity, lots of pull. Low electronegativity, not a lot of pull. Okay, so that's what's up with the electronegativity table. If you look at the notes page on your favorite website, dorvillemhs.com, you're going to see a big table. You could also simply Google electronegativity table and one will show up. So you can look at the values. Alright, and then up here, just a little review. We did Lewis dot structure, and we talked briefly about the difference between covalent and ionic compounds, and so we're going to get into that in more detail. So, electronegativity, what is the most, so you should get this, pull this up in another window, okay, and see if you can answer these questions. What is the most electronegative atom? what groups bond well with halogens, and what group has a low negative electronegativity, and what does this mean? I'm going to pause and see if I can pull up an electronegativity table, and you're going to look at one and see if you can answer those questions. All right. Okay, and we're back. So, if you just went and looked at a big electronegativity table and tried to answer these questions for yourself, good work. If you didn't and you just watched right through, shame on you. You are not taking advantage of your education in the way that you should. So, what is the most electronegative atom? Looking at the electronegativity table, I see fluorine, chemical symbol F, having an electronegativity value of 4. And that is the largest listed. It looks like oxygen has the second largest at 3.5. And then chlorine and carbon. Wait, chlorine is 3.0. Carbon's a 2.5. Bromine a 2.8. Okay. So, out of all the elements, fluorine wants an electron more than any other element. Now, what groups, again, groups are these columns, all right, what groups bond well with halogens? So, these are halogens, and the halogens want electrons very badly, so the group that would bond well with them would be these. Okay, so we have the alkali metals, the alkaline earth metals, transition metals, but the alkali metals have one valence electron to donate. These want to take in that electron, and so these will bond well together. So the answer would be the alkali metals. Okay. For example, sodium is right here. Where is it? And chlorine, NaCl, that is table salt. So salt is in all the processed food that we eat, and sometimes we even put it on our food. So, if we were to draw Lewis dot structures, chlorine has 7 valence electrons, so I'm going to draw 7 electrons around it, and sodium just has 1. It has electrons in its inner shells, but 1 valence electron. So, chlorine is so electronegative, meaning it pulls on the electrons so much that instead of a sharing of these electrons, it actually pulls this away from sodium. So sodium kind of gives this electron up. It says, here, chlorine, you can have it. Chlorine now has 8. 1, 2, 3, 4, 5, 6, 7, 8. And sodium, having lost that electron, reverts back to a full shell. So the shell that is inside its valence shell is now full. It has lost its 1 valence electron. And so the way we write that is Na plus and Cl minus, indicating that these two are joined together, and we're going to learn about atomic bonds in a moment, but sodium has lost an electron and so has a positive charge. Chlorine has gained an electron and so has a negative charge. And they are happy in that situation. Okay. Next question, what group has a low electronegativity, and what does this mean? A low electronegativity would be the alkali metals and the alkaline earth metals. So alkali plus alkaline earth metals. And what this means is that they want to donate electrons. They want to donate electrons. They are ready to get rid of those so that their inner shell becomes their valence shell, and they are then happy or stable. Okay. So we're going to stop this and then do page 2 of these notes in part 3.